This is a really good question for two reasons. I like it because it's a two-unit question. Someone asked it to me in the middle of class when we were doing revision, and it's straight out of a two-unit paper. And it illustrates really well the fact that the two-unit course is not an easy course in itself. If you're an Extension 1 student, you can often get caught up in trying to understand all the three-unit concepts and the three-unit methods because they're trickier, particularly under trig, auxiliary angle and general solution and all the trig expansions or perms and coms. People focus on that to the neglect of the two-unit course, and then they don't do well on the two-unit exam. They wonder why. So firstly, just to show that there's lots of good, interesting kinds of problems in the two-unit course, and secondly, it's a hard question, but it's hard in the right way. This is what I mean. Before I became a teacher, I just had two categories for questions. They were either easy or they were hard. But now I realize there are lots of different ways for a question to be hard. For instance, if I gave you, or like say, when do you learn Pythagoras? Like in year 7 or something like that. If I gave you a question like x centimeters, and let's put some numbers on this. 2.71. Okay, if I gave you that question and said, find the value of x, you could do it. It would be hard, but it would be hard for a silly reason. It would be hard because the numerical values I gave you make the question difficult and they require a lot of arithmetic precision. And then it's not hard because it tests your understanding of Pythagoras. It's just hard for hardness sake. So this is not a good question. It's hard, but it's not a good question. This one, on the other hand, is hard in a very clever way. So let me try and illustrate that. It's a two-parter. So firstly, we have to prove similarity, and secondly, then we have to evaluate this length down the bottom. Okay. So let's do the similarity proof first. It's quite trivial. So what are you given in the question? ABC is isosceles. The equal sides are length 1. You're also given this angle down in the corner, and you're told that BD bisects this other angle that's opposite, the base angle. So therefore, right away, we can say things like, for instance, CBD is 36 degrees, and ABD is also 36 degrees. Okay? Because number one, it should be the whole angle is 72 because equal angles rather are opposite equal sides. And secondly, they're both 36 because it bisects. Okay? Because you've got 72, you can use the angle sum of a triangle to work out that this one up here is going to be 36 as well. And that's almost all you need. Because you can say, look, in triangle ABC, and getting the order of the letters right, BCD, you've got angle BAC being equal to angle CBD. We just showed that both of those were 36, right? So I would have probably, if I'd done this properly, I would have proven that above and written it out. But I'm not sort of focused on the similarity part of this proof because I think it's quite straightforward. And secondly, you've got angle DCB. Now that 72 is actually in both triangles, right? So I just say that angle is common. Once you've got two angles being the same, the third angle must also be the same because of angle sum of a triangle. Therefore, that's all you need to show that these are similar. And the reason is equiangular. Okay, so far so good. Now when you get to the second one, things get a little trickier because there's so little actual length information given to you in the question that you sort of wonder where to start. You may think, you might have the idea that this has to do with trig, okay? Because you've got all these different angles here. You do have that length over there. You might notice that because these triangles are similar, you've got equiangular, right? You'll find that this angle is also, sorry, not 36, it's 72. So down the bottom here, you've got another isosceles triangle. So you have this side and this side being equal. So then you might notice that, okay, if that's x, then this should also be x, right? Then you might look up in this top triangle, A, B, D, right? And you'll see, okay, 36, that leaves me with 108. Could have seen that through the straight line as well. So you might be tempted to use sine rule. Sine rule is not that bad an idea, actually. When you think about it, you've got x over the angle that's opposite is sine 36. Right? And then your other side is 1 over sine 38, sine 108, sorry. 38. Okay, so therefore you get an expression for x, which seems like it's a good start. But it turns out that this is not actually that useful if you want an exact value. I mean, you could evaluate this and you'll get the correct length. That's a true statement. But if you want something precise, 36 and 108 are not great angles to work with. In fact, you can work out the exact values for sine 36 and hence 108, which is 3 times bigger. But you end up either having to use a regular pentagon or the golden rectangle because the golden ratio is involved. And it's more effort than it's worth to work out what sine 36 and sine 108 are. Okay? So how do we go about this? Trig is not involved. Okay? Even though like it's sort of a red herring, you've got all these angles here, but trig isn't there. So how do we solve this? Okay, what I'm going to do is, often with similar triangles, one of the hardest things is about vision, about seeing how the triangles relate to each other. Okay, so to help us, I'm going to draw the two similar triangles, but I'm going to draw them separate. You can see they're on top of each other, right? So if I separate them out, things will be a little easier to see. So you can see here, if I do the big triangle, that's A, B, C, okay? You've got your 72s down here, and your 36 up here, your 1 and your x, okay? Now, what I want to try and do is get the two triangles next to each other and orient it in the same way so that I can compare the right features, right? So, the other triangle, BCD, should look like this. And put it upright, okay? I've got my two 72s, so you can see I've actually sort of rotated this around, okay? And that gives me the 36 up the top. Now, what are the sides that I'm interested in here? Well, I've got x and x over here. That's all I got so far. Okay? Now, on the face of it, it doesn't look like there's much that's useful here for solving x, but this is one of the reasons why this question is hard, is because you sort of have to pursue this line even though it's not obvious why. Okay? So, what can I know about similar triangles when I've got these lengths? Well, I know that there are some sides that are in proportion, right? So, for instance, I could say CD on BC. So that's this side here in the smaller triangle to this side here, okay? That ratio should be equal to this longer side to this longer side, right? BC on AB, okay? And of course, when you're doing this rigorously, you would say in similar triangles, corresponding sides in similar triangles are in the same ratio, okay, or in proportion. So now if I put in some values here, right, I know what these values are. BC is x, BC, again, is x, and AB is 1, okay? So I have this now. This is x squared, okay? So I have x squared over here. Okay, now, by the way, this sort of makes sense if you want to visualize it or think about it this way. This triangle is like this triangle, but it's x times smaller, okay? You can see I went from 1 to x, and therefore I should go from x to x squared. That makes sense, okay? Now, when you come back to our original triangle, how is this useful to us? Well, now I have x squared over here, okay? And that tells you that because this whole AC, right, is 1. Therefore, AD, which is left over, is 1 minus this part here. So it's 1 minus x squared. Okay, 1 minus x squared. Alright, now we're almost there, okay? Remember, this is just a two-unit question, right? So there aren't many complicated geometric properties that we need to use here. The last one that I'm interested in is that ABD. ABD, can you see it there? That's also an isosceles triangle. You've got 36 and 36 here, okay? Therefore, you've got AD and BD being equal. Okay? AD and BD equals BD. And the reason why is because equal sides are opposite equal angles. by the way, especially in a question like this, where you've got 50 million triangles flying around everywhere, if you're talking about some features of a triangle, you should name which one it is, okay? So the triangle I'm interested in is ABD. Okay? Therefore, I've got x and 1 minus x squared being identical. So if you like, BD is kind of like the hinge, right, on which this question sort of turns. I'm trying to get to that side from two different angles. So from this side, I saw that it's x. From this side, I saw that it's 1 minus x squared. Okay, and you can see the importance of proving similarity in the first part. Okay, I'm almost there. This gives me a quadratic, okay, which is x squared plus x minus 1. Okay, so if you go ahead and solve this, because it can't be factorized very nicely, right? You've got minus, I'm using quadratic formula, right? Minus b plus or minus the square root of b squared minus 4 ac, okay, all over 2. So just doing a bit of simplifying there. Now you can see here, as with most quadratics you'd expect, you get two solutions, right? But you know that x is a length, right? So therefore it must be positive. So therefore you can reject one of these solutions, namely the one which says minus 1 minus root 5. You don't even have to know what root 5 is as a value, you know, it's between 2 and 3, to know that a negative number minus another number will still be negative, okay? So therefore, x can't be equal to minus 1 minus root 5 on 2. Okay, it has to be equal to the other one. So this is my answer, minus 1 plus root 5 on 2.